Hello everyone. Welcome to this online session. Previous to this, we have discussed example of diode based circuit which was rectifiers. Rectifiers were primarily used to convert AC into pulsating DC, and it was basically the part of a DC power supply. Today, we would try to look at one more popular example of diode based circuit, which is a clipper circuit. Let us try to understand what basically a clipper circuit is. If we try to go to the definition of clipper circuit, trying to understand it, then clipper circuits are those circuits that restricts some part of input signal to pass to the output and allows the remaining part to pass without distortion. What do I mean by this? What do we mean by this is that clipper circuits are the circuits to which if you give some input signal, then some part of input signal would be available at the output and the remaining part would be restricted and would not be available on the output side. To understand this better, let us try to look at one example with which we are familiar. Most of you would be able to identify what this circuit is. This is basically a half wave rectifier. Yes, we are more used to see this circuit with a transformer which is connected between A and B. But what is the voltage at the secondary of the transformer? The voltage at the secondary of the transformer is Vm sin omega t. So if I say that this is the input voltage which we are giving to this circuit, then this is something similar to Vm sin omega t, right? So with this diode and with this RL, if the sinusoidal input is given between A and B, this is basically the circuit of a half wave rectifier. And how does this circuit behave? We understand that in positive half cycle, terminal A would be positive, B would be negative, and hence diode would be forward biased. In forward bias, it would act as a closed switch, allowing the current to pass. And considering diode to be ideal, there would not be any voltage drop across the diode in forward bias. And hence, whatever is the input voltage would be available at the output. So, during the positive half cycle, the complete voltage would be available in the output. Whereas, in the negative half cycle, that is when A is negative and B is positive, diode would be reverse biased. It means that it would act as an open switch. If it acts as an open switch, there would not be any current that would be passing, and hence the voltage across RL would be zero. In that case, my output voltage would be zero. Thus, what is the type of output waveform that we get? The type of output waveform that we would get would have a positive half cycle, whereas the negative half cycle would be restricted. So now, if we try to see this in context with clippers that we have defined, then what does this circuit do? This circuit allows the positive half cycle, that is one portion of the input signal, to be available at the output without any distortion. Whereas it restricts another portion of the signal, which in this case is a negative half cycle. Yes. So if we try to remind ourselves with the definition of clipper circuits, then clipper circuits are those circuits that restricts some part of input signal to pass to the output and allows the remaining part to pass without distortion. Again, in this case, positive half cycle is passed, negative half cycle is restricted. So this is what we mean by clipper circuit. By the word clipper, the word clipper comes from the word clip. Clip means to restrict the movement. No, we clip the paper so that it does not move around here and there, right? So Clippers are the examples of diode-based circuits. Clippers primarily consist of diode, resistors, and DC supply. Now, depending upon how different components are connected in a circuit and which part of the input is restricted on the output side, clipper circuits can be classified in number of ways. For example, we can have a series clipper where the diode would be in series with the load resistance. Similarly, we can have a shunt clipper where the diode would be in parallel to the load resistance. It means that the output would be taken across the diode. Going further, we can have a positive clipper if the clipper circuit restricts the upper portion of the input signal. By positive, what we mean is the upper portion. If it restricts the upper portion of the input signal, we would call it as a positive clipper. Similarly, if the clipper circuit restricts the lower portion of the input signal, that is the negative portion of the input signal, we would call it as a negative clipper. If we have a clipper circuit which restricts some of the positive part as well as some of the negative part, then we would call it as a dual level or a combinational clipper. We are going to see examples of each of this, so nothing to worry much about this. Just it is for the sake of classification that we are listing all different types of clipper circuits. Going further, we can have an unbiased clipper. Unbiased clipper means a clipper circuit that consists only of a diode and a resistor, and it does not consist of any voltage source. Similarly, I can have a biased clipper where the clipper circuit would consist of a voltage source along with diode as well as resistor. Right? So I can have different types of clipper circuits as listed here. In popularly, we would have combinations of this. It means that I can have a biased positive series clipper. I can have a biased shunt clipper, something like this, right? If we talk about applications of clippers, then clippers basically falls under the category of waveform shaping circuits. It basically gives some kind of shape to a waveform, and they are used in waveform generators. Say for example, if we think of a sinusoidal waveform or if we think of a square waveform, they are relatively easy to get. But suppose that if we talk about a trapezoidal waveform, no, we are aware about a trapezoidal shape in geometry, a trapezoid. So if I want to have a trapezoidal waveform, then maybe we would be able to obtain such waveforms using clippers. Further, clippers are also used as signal limiters or protection circuits. Suppose that I have a circuit and I want to assure that the input to this circuit should not go beyond this value. Anything coming beyond this value should be restricted. Right? This may be required to protect the circuit from getting into some problem. Right? So clipper circuits are also used as signal limiters or protection circuits. Fine. Let us start studying different types of clipper circuits. Popularly, what is we would try to divide clippers in two types, series and shunt, and we would take examples of this. What do we expect to be asked in examination on this is that you may be given, most probably you would be given a circuit for which you are supposed to identify the operation of the circuit. That is, for the given input waveform, you are supposed to find what would be the output waveform. So let us start with a known example of a series clipper. I would again take the same example of half wave rectifier. We have discussed this. What happens is that the positive half cycle is passed on the output, the negative half cycle is not passed, it is restricted. So now if I want to categorize or classify this clipper, or if I want to give name to this clipper, then first of all we would say that we have a diode which is in series with RL. So this is an example of a series clipper. And if we see the output, then the negative part of the waveform is clipped, the positive part is available, and hence we would call it as a negative clipper. So combinedly, this is an example of negative series clipper. I'm sure you are getting this. Now let us try to see more examples of clipper circuits, right? In the same category, let us try to take one more circuit. Let us say that we have this circuit of a clipper. If we try to compare it with the previous example, we have reversed the position of the diode. This actually is an easy example to solve, but as we go ahead in this presentation, we will try to take examples which are more complex. Whatever be the complexity of the clipper circuits, if we try to identify the method with which we can analyze the circuit, then we would be able to surely get an answer. And here I would try to use a three-step method to solve any clipper circuit. And this is what we would be using for this simple example also. What am I trying to say? That we would go with three steps of analysis for given clipper circuit. And if we are able to go through these three steps correctly, we are bound to get an answer, right? So let us try to look at this circuit and let us try to go for this three-step method. So what is the first step? First step is that for any given circuit, try to identify what would be the output voltage when the diode is on and when the diode is off. Now, if we try to see this, irrespective of the input, we are not focusing on the input right now. Just try to focus on this circuit and try to find what would be the output voltage if the diode is on and if the diode is off. Suppose that this diode is on. When the diode is on, it acts as a closed switch. Considering diode to be ideal, there is no voltage drop across the diode. So here we find that whatever is the input voltage present would be the output voltage. Why? Because this acts as a short circuit, this acts as a short circuit. So input voltage and output voltage would be same. So what is the conclusion? The conclusion is that when the diode is on, output voltage would be same as input voltage. Similarly, this is what we write. When the diode is on, it acts as a closed switch, so output voltage is equal to input voltage. Similarly, when the diode is off, it acts as an open switch. And when it acts as an open switch, there would not be any current which would pass through the circuit. If there is no current which is passing through the circuit, the voltage across RL, which we call it as V0, the voltage across RL would be 0. Because what is voltage across resistor? It is current multiplied by the value of resistance. If the switch is open, that is the diode is off, there is no current which is flowing. And if there is no current which is flowing, the output voltage would be 0. So when the diode is off, it acts as an open switch and no current flows. So V0 is equal to 0. So we have done our first step, which was to identify the output when the diode is on and when the diode is off. And this is irrespective of the input. Now, let us try to relate input with diode. That is, in step 2, we try to identify that when would diode be on and when would diode be off. Now, for diode to be on, what do I mean by a diode to be on? It means that it needs to be forward biased. And what do we need for diode to be forward biased? For diode to be forward biased, we need that the voltage at its anode, that is P terminal, should be more than the voltage at the cathode, which is N terminal. That is, your Vp, that is your anode voltage, should be greater than your cathode voltage. In that case, the diode would be on. Now, in this case, what would happen? What would happen is that when you would have a positive half cycle, this would be positive, A would be positive and B would be negative. So what is the voltage available on the N terminal of the diode? Positive voltage. And what is the voltage available at P terminal? Negative voltage. So here what it means, that voltage at P terminal are less than the voltage at N terminal. Why? Because N is positive and P is negative. So the diode would be off. So here we write the diode would be off during positive half cycle, A positive, B negative. That is, when input voltage is greater than 0, diode is off. Similarly, in the negative half cycle, A would be negative, B would be positive. So the voltage at P terminal would be positive, voltage at N terminal would be negative, and hence diode would be on. It would be forward When in the negative half cycle, B is positive and A is negative, that is input voltage is less than 0, diode would be on. So now in these two steps, what we have done, we have identified that if diode is on, what would be the output voltage? If diode is off, what would be the output voltage? In the second step, we have identified that if this is the condition of the input, diode would be on, and if this is the condition, if this is the condition of the input, diode would be on, and if this is the condition of the input, diode would be off. So the from these two steps, we will go to the third step, that is estimating the output waveform. So what do we identify here? If input voltage is greater than 0, that is positive half cycle. If input voltage is greater than 0, what is the case? If input voltage is greater than 0, diode is off. So diode is off. And if the diode is off, what is the output voltage? The output voltage is 0. So for input greater than 0, output would be 0. Similarly, for input less than 0, diode would be on. For input less than 0, diode would be on. And if the diode is on, what would be my output voltage? My output voltage would be same as my input voltage. So if we now try to sketch the output waveform, you would get something like this. That is, in the positive half cycle, when Vin is greater than 0, output voltage is 0. You can follow my cursor. When Vin is greater than 0, that is in the positive half cycle, my output is 0. Whereas when Vin is less than 0, that is in the negative half cycle, my output is same as Vin. So my output is same as Vin. If we want to name this clipper, then because diode is in series with RL, we would name it as a series clipper. From the output, because positive portion, the upper portion of the waveform is clipped, we would call it as a positive clipper. So combinedly, we call it as a positive series clipper. Maybe at this point of time, if you want, you can pause this slide, you can pause this presentation, and you can look at the example once again so as to understand clearly what is my step 1, step 2, and step 3. Once we are done with this, we may proceed with the next example to study. Again, a next example of a series clipper where I am introducing an additional element of a DC power supply. So I'm going to the next level of complexity. I'm adding one more level of complexity to the circuit where I have a diode, I have a resistor, and I have a voltage source. Whatever be the complexity of the circuit, our approach for solving this would remain same. Right? It means that we would again follow the 3-step process. Here, we again assume that the input voltage to this clipper circuit is a sinusoidal signal, and we again have or make one assumption that this battery voltage is the DC source VB. We assume that these voltages are less than the maximum voltage available at the input. So in this sinusoidal input, if I say that my maximum voltages are 10 volts, then VB is less than 10, right? VB is less than 10. This is what the approximation that we make here. Fine. Let us go with the 3-step process. What is our first step? Our first step is to identify that irrespective of the input, what would be the output when the diode is on and when the diode is off. Fine. So if the diode is on, let us try to understand this. It acts as a closed switch. Again, considering diode to be ideal, this acts as a short circuit. This itself is a short circuit. So Vin and V0 are same because they are in parallel. So output voltage would be same as input voltage. This would be the case in all series clippers. When the diode is on, the output voltage would be same as the input voltage. When the diode is off, it acts as an open switch. No current passes through this. The voltage across RL would be 0. So this voltage is 0. Now if we consider V0, then V0 is nothing but it is summation of voltage across RL and this VB, the battery potential. right? Now the voltage across RL is 0. So what would be V0? V0 would be same as V. Yes. To summarize, we write these 2 points. When the diode is on, it acts as a closed switch. V0 is same as input voltage. When the diode is off, it acts as an open switch. No current flows, no voltage drop across RL. So V0 would be equal to V. Having done this, let us move on to the second step. What is the second step? Identify the condition for the diode to be on and off. It means that with respect to input, when the diode would be on and when the diode would be off. Again, let us remind ourselves that diode is forward bias, diode is on if the voltage at P terminal is higher than the voltage at N terminal. Now let us try to understand what is the voltage at P terminal. V in input voltage is available at P terminal. And what is the voltage available at N terminal? The voltage available at N terminal is VB, because this is directly first connected with VB. So diode would be on if Vp is greater than Vn. Here Vp is input voltage and Vn is Vb. Thus, diode would be on when input voltage is greater than Vb, satisfying this condition that Vp should be greater than Vn. Diode would be on when input voltage is greater than Vb, input voltage is greater than Vb, and diode would be off if input voltage is less than Vb. There should not be any doubt in understanding this. The voltages at N terminal is plus VB, so you need to give voltages higher than VB on P side. At that time only the diode would be on. It means that the input voltage should be higher than VB. At that time only the diode would be on, otherwise it would remain off. Now, having done this step 1 and step 2, we may go for the step 3, from which is estimating the output waveform. So what is the case? What is the case is that if input voltage is greater than VB, diode is on. And if the diode is on, output voltage is same as input voltage. This is what we have marked here. Similarly, if input voltage is less than or equal to VB, diode is off. If input voltage is less than or equal to VB, diode is off. And in this case, my output voltage would be same as VB. Let us try to put it in terms of the waveforms. See, this is the input waveform that I have seen, that we have shown. This is the same as this waveform. What I have done additionally is that I have drawn a line of VB. VB would be some finite voltages. It is a DC voltage, so it represents a straight line. So this is the VB voltages. So now, if I compare input voltage with VB, then I can divide input voltage in 2 parts. The part of the input waveform which is above VB, say this part or this part, this is the part of input waveform which is greater than VB. So Vi is greater than VB. Whereas this portion of the waveform, is the portion where input voltage is less than VB. So in this part, when input voltage is greater than VB, diode would be on, and diode would be on, hence output voltage would be same as input voltage. So in the output, you should expect this to be present. Whereas in this part of the waveform, diode is off. And hence the output voltage should be constant at VB. So in this part, you should not get this part on the output side. Instead, you should get a straight line which is at the level of VB. So if you try to draw the output waveform from this, the output waveform would appear something like this. When the input voltage is higher than VB, our output is same as input. Whereas when the input is less than VB, this part of the input waveform is clipped, it is restricted. Instead of this, what we get is a flat line at the level of VB. Right? If you try to name this clipper, then this obviously is a series clipper. Again, it is restricting the lower portion of the waveform. Yes, Some of the positive part of the waveform is also restricted, but in general we say that a positive clipper is one where the upper portion of the waveform is clipped. Negative clipper is one where the lower portion of the waveform is clipped. Here the upper portion of the waveform is something which is available. The lower portion of the waveform is something which is clipped. So we would call it to be a negative clipper. And third, the circuit is making use of a DC source and hence it is a biased clipper. So combinedly, we would call it as biased negative series clipper. I am sure this should be clear, right? Again, if you want, you can take a pause here. You can go through this slide once again, and you can understand all the three steps. Once you are done with this, we may proceed with the next example. This is again an example of series clipper where I am again introducing a DC voltage source and a diode is present, but compared to the previous circuit, I have changed the position of the diode. I have made the position to be reversed. At this point, I would like you to solve this circuit. Solving this circuit, we need to work in these three steps. So at this point, I would like you to pause the video. Take pen and take your notebook and pen with you. Try to draw the circuit and try to estimate what would be the output waveform. Right? It would be, does not matter whether you get a correct answer or not, but you would at least get the clarity of thoughts and you would able to identify that what is the problem that you are facing, at what point you are getting stuck. Yes, so I would request you to pause the video and try to solve it by your own. Fine. I'm sure you all would have done this, and I'm sure many of you would have got the correct answer. Let us try to discuss this here. So first we try to identify when the diode would be on and when the diode would be off. This is a series clipper. So the condition remains same. If the diode is on, output is same as input. If the diode is off, output would be equal to VB. So this is what we write. When the diode is on, it acts as a closed switch. V0 is equal to Vin. When diode is off, it acts as an open switch. No current flows and output voltage would be equal to V. Fine. The second step, we try to identify that when diode would be on and when diode would be off. Again, we know this, that for diode to be on, the voltage at P should be higher than the voltage at N. Here, what are the voltages at P? Then terminal P is connected with VB. So your VP is equal to VB. And what is the voltage at N terminal? At N terminal, the voltage is equal to input voltage. So if your input voltage is less than VB, what we want, VP should be greater than VN, right? So if VB is higher than VN, then diode is on. And if VB is less than Vn, then diode is off. It means that if input voltage is less than VB, if input voltage is less than VB, then diode is on. And if the input voltage is greater than VB, then the diode is off. Right? From step 1 and step 2, let us try to evaluate the waveform. So when the input voltage is less than VB, the diode is on. The diode is on. Output voltage would be same as input voltage. But when input voltage is greater than VB, diode would be off. And when the diode is off, output voltage would be same as VB. Let us try to understand this in terms of the waveform. So again, I have brought the input waveform here and I have drawn the line of VB. Again, we are dividing input voltage in two parts. The part of the input above this line is input voltage greater than VB. The part of the input below this line, it means that this waveform input voltage is less than VB. Now what we find here, if input voltage is less than VB, it means that if the input voltage is less than VB in this portion, the diode would be on and the output voltage would be same as input voltage. So you expect this portion of the input waveform to be available on the output side. Whereas this portion of the waveform or this portion of the waveform, when input is greater than VB, diode is off and output would be equal to VB. It means that we would not be able to see this waveform. Instead, the output voltage would be fixed at VB. So let us try to draw the output waveform. So the output waveform would look something like this. When the input voltage is higher than VB, the output voltage is restricted and it remains constant at VB. But when the input voltage is less than VB, the input voltages are available on the output side. So again, if you try to name this, what we would name, I'm sure you would be able to get this. We would call it to be a biased clipper because battery is present. We would call it as a series clipper because diode is in series. And because the upper portion of the waveform is clipped, we would call it to be a positive clipper. So what we have is biased, positive, series, clipper. Fine. So these examples that we have discussed are the examples of series clipper. In the next section, what we would try to look at would be some more examples of clippers where we would take examples of shunt clippers. Again, one should be clear that there can be many manipulations which are possible in this circuit. I may reverse this polarity of the battery. It means that instead of positive and negative put in this form, I can reverse it. So that in the upper I would have negative and in the bottom I would get positive. Whatever be the circuit, if we follow these three steps and if you are clear about these three steps, you are bound to get an answer. Again, it might also happen that the input voltage which is given to you may not be sinusoidal. It may be triangular waveform or it may be square waveform, right? Again, that does not matter to us. Whatever is the shape of this waveform is not important. We need to identify that for the given shape of the input, when the diode is on and when the diode is off. And if we are able to identify this correctly, there should not be any issue in getting the answer. Fine. We stop here. Thank you for watching this. In the next presentation, we would start with the examples of shunt clipper. Thank you.